7:30 starts. So last time we talked about pipelining. That's the introduction to the structure. And we went over a pipeline data path. And today we're going to go over pipeline control. Before we go straight into control, we just have a couple more things to not cover as new things, but we've seen the multi-cycle pipeline diagram already. But we didn't look at it in as much detail as the single cycle pipeline diagram. So here is an example of multi-cycle for multiple instructions. And so on this axis, we have the clock cycle number. So it's clock cycle 1, clock cycle 2, all the way to 9. And then here in each row of this table, we would have our instruction. So we start with the load word. And like we talked about, pipelining does not decrease instruction latency. The load word still takes all 5 stages, right? So we have in clock cycle 1, we fetch from instruction memory, load word. And in clock cycle 2, this is where we're increasing our throughput. Rather than only doing the load word is done with the instruction fetch stage, and it's in the instruction decode stage. And everything that it needs was saved to this pipeline register. So now the next instruction can be fetched at the same time. Okay, so clock cycle 2, we have 2 instructions, one in decode, one in instruction fetch. Clock cycle 3, load word is in executes, subtract is in decode, and add is in fetch. Clock cycle 4, load word is in memory, subtract is in executes, add is in decode, and second load word is in instruction fetch. And then clock cycle 5, our load word, the first one, finishes in write back. And our sub, even though it doesn't do anything in the memory stage, it still occupies the memory stage. And we talked about why we do that. Why do we do this?
It gets skipped to the next instruction.
Yeah, it's not so much to be skipped, but so that we can keep track of which resource. Because if we skipped the memory stage and went straight to write back, then we're conflicting with the previous. So that's why, even though we don't do anything in memory, we still occupy the memory stage. It doesn't help us with performance if we skip the memory stage, and it only complicates resource sharing. And then in the same cycle, we have the add in the execute stage, the second load word in our instruction decode stage, and then this add is being fetched. So once we get to this clock cycle 5, our pipeline, our entire data path is being fully utilized. And once we're here and the pipeline is full, every single clock cycle, we finish an instruction. Finish an instruction. Finish an instruction. Finish an instruction. Right? And assuming all of these 5 pipeline stages were evenly distributed, we're about 5 times faster compared to just single cycle. Right? So this is the diagram that you will need to know how to create, how to read. And you don't have to draw these different stages. Instead, you just say IF is instruction fetch, ID is instruction decode, EX is executes, M is memory, WB is memory. So you would create this table, fill it out with those different stages for each instruction. And we'll revisit this again when we talk about those hazards, being data dependency hazards and control hazards. And then this is just, again, highlighting that once we're in cycle 5, we filled up the pipeline. And now every single cycle, we fetch a new instruction, completes an old instruction. So we have this overhead of the time to fill the pipeline, but once the pipeline is full, one instruction is completed every single clock cycle. So just like single cycle, our CPI is approximately 1. It's not going to be exactly 1 because of this time to fill the pipeline, but it's approximate, especially when we have high instruction count, okay? When we have instruction count in the billions, the +4 cycles that it took to fill up the pipeline is negligible. So back to what a single cycle pipeline diagram would look like. For a single cycle pipeline diagram, we have the entire data path that is drawn. And we're specifying what instruction is in each stage of the pipeline. So this was our first load word, right? This is the subtract. The add is in executes. Second load word is in decode. And this add was in instruction fetch. So this is from the same instructions that we were looking at with the multi-cycle diagram, but this is specifically looking at the 5th clock cycle, right? In the 5th clock cycle, had the load word and write back, sub and memory, add and executes, the second load word and decode, and then the last instruction, which was the add in instruction fetch. So it's specifically zooming in on this 5th clock cycle. And then when you have this, you can ask questions like, in the 5th clock cycle, what is the data read from the register? It's register 1 is RS, and we're not reading RT. Okay. Well, it is read, but we don't do anything with it, right? We don't need to save it to the register file. We're not using it for load word, except for that it's going to be the right register that we saved in here. All right, so we can now move on to pipeline control. So no information transfer from one pipeline stage to another is possible except through those pipeline registers. And that's for now. We'll talk about how this is going to be possible in the future. So that means that everything that happened in any previous stage will be overwritten, right? When this load word is in decode, it's going to overwrite all of the information that the add was using during its execute. And this add will overwrite everything that was used for the decode stage of this load word. Right? So if you need anything for your next stages, you better save it into the pipeline register ahead of you. Okay. So by doing that, all of the data belonging to one instruction is kept within the stage that the instruction is in. So that means that our controller information should travel with the instruction along the pipeline stages, just like the data. And we already went over this. So here is our data path with now our control signals are added, right? So this was the mux that we were missing before, right? Register decimal. We didn't have a signal to say if we're going to write to the register. We're missing this mux for ALU source, the branch, AND gate, PC source, mem to reg, right? These are all the same signals from single cycle. We know what all of these are for, right? So now the question is, since we have all of these control signals, where do we generate them? And how are we going to save them to have it follow the instruction? So where should we generate these control signals? Is there one place, or should I just calculate it every single time I need them?
Stage.
Hmm?
In the decode stage,
Why the decode stage?
because the execution is the first one that actually like uses the control signals. I think it was.
That's true, but
So that's like the first one where it would like the one right before it's the one where it would like you'd save it and then it'd matter for the next one.
so it executes the first stage. So why don't I just calculate it and execute it?
Because it would be overwritten by the next one, isn't it?
I can carry all my information with me, right? So like whatever I need, I just need to save it into this register. So that I'm just trying to hint that there's a more important reason that we do it in decode.
We also need to do whether we write to the register as well. And that's in the decode stage,
You're talking about this control signal?
right?
So this one, but this needed to follow with the instruction that's actually in the write back stage, right? So when we're in the decode stage, we're kind of sharing the register file with write back, but we don't have any information about that instruction within this stage. It needed to be calculated and followed with that instruction. And then out of this memory / write back register, that reg write signal would come. So why do I want to do decode stage? What am I consuming in the decode stage? I have the instruction. What about the instruction am I using?
Assume the execution part going into the next one.
Yes.
Like there's I know from like the homework quiz, there's like the three things that gets moved over from the control. And one of those gets consumed and we don't save it on the next part of it. I'm trying to remember which one it was.
Not sure.
Okay, I might be wrong then.
What are we consuming? What am I doing here?
All the instructions,
What is this?
that's RS.
RS, right? And it's coming from directly the instruction, right? Same with RT, right? Do I need this information ever again? Do I need to know what RS was or what RT was?
Possibly.
Okay, right now, for now. Well, actually, no, I never need to know what this was. After here. I don't need to know what RS was. Maybe RT, because it could be a destination. But because I consume it, do I save it to the pipeline register? I don't need to, right? So that means I can save less data into this register by consuming everything that needs to be consumed. So what else should I consume from the instruction that is used to calculate my controls?
Assign extended immediate.
That's here. But that's used to calculate controls specifically. What is used to calculate control?
The coded, the function coded here.
Opcode and then funct code is used over here. Right? You see this one? Funct code goes down here. Or it's over here. And it's just shown as it's part of this. Right? Because it's from instruction, what is it? 4 to 0, or is it 5 to 0? Yeah, 5 to 0, because it's 6 bits. Right? And it's consumed here. But opcode, which is instruction 31 through what, 28? The top 6 bits, right? That is used to calculate things like reg write, ALU source, ALU op, regdest, branch, PC source, memwrite, memread, memtoreg, right? It calculates all of those. So if I take those 6 bits from the instruction, calculate control here, and then just save these control signals into the register, then I can throw away opcode. I don't need it anymore. Okay. So it's just convenient to put it here and then throw away opcode, just like how we're going to throw away RS. So these are just recalling the different control signals. Right. And it's talking about for the different stages, what are the control signals for instruction fetch? It's the same for all instructions for decode. I don't need any specific control signals for decode. But for the execute phase, which is the first phase that you talked about, that we're actually using these control signals, right? Because I need to know what is my register destination. I need to know what is the ALU op. This is the 2-bit code that is calculated again from opcode. What is my ALU source? Is it going to be the data from RT, or is it the sign extended immediate? In the memory stage, we're consuming branch. Is it a branch? Mem read, mem write. Write back. We're consuming mem to reg and reg write. And we're also consuming this register. Well, in a way, we're consuming it in write back, but the reason that it's in execute that we're consuming it is because that's when we're consuming the control signal. This is where the decision is made. Is it RT or is it RD? So once we consume this, we don't need this control signal anymore. And what we're saving instead now is just RT or RD as register destination. And then this is just, again, a summary of those different control signals. And this was the table from the previous lecture as well. So previously, our control signals were derived from the instruction in the single cycle implementation. And we're gonna do it the same way, right? So we have that same control block. It's just in the decode stage. We get opcode from the instruction. And then we're gonna calculate all of our control signals. And then now we have them split up between these are the signals that will be consumed in write back. These are the signals consumed in memory. These are the signals consumed in execute. And then when the instruction goes into execute, it has all of the control signals that it needs for all of its future stages saved into the pipeline register, and it's going to consume the ones needed for the execute phase. And then because I'm done with the execute phase, into the next pipeline register, I don't need to save my execute control signals anymore, right? I'm done with them. But I need to save what I'm going to use for memory, what I'm going to use for write back. I consume what's for memory. I only save what's for write back because I've used my memory control signals. And then I go back over here towards the decode stage to write back if I was going to write back. So we can see that all of the control signals follow the instruction, right? Just like all of the data that's needed for the instruction follows the instruction. So here is the data path with now control signals added to it. Okay. So they're calculated in decode, saved here, executes consumed. And what are we using in executes? Is it RT data or is it sign extended immediate? What is ALU off? Right? And that's determining along with funct, what is the ALU going to do? And then what is my register destination? Is it RT or is it RD? And then once I have these results, right, this will tell me was my results that I needed RT or was it RD, and I can save that as my destination register. And then I don't need register dest anymore. And then once I figured out what the ALU was going to do, and it did its calculation, and which operand is the second operand, I don't need ALU source, I don't need ALU op, I don't need func code. I only need what is the result from the ALU. And then this is the adder for what function, and a function. It is an I type, but specifically what I type? Yeah, the branch. This is my target entry, right? So for every single instruction this is calculated, it's just, I'm only going to utilize it if I am the branch. And even if I am a branch, I still have to figure out, do I need to actually branch to that or not? And then same thing in memory, I'm consuming, do I need to write? Did I need to read? Am I a branch? And if I am a branch, was the zero flag also zero? And then that would be used to change PC. And then I'm done with these controls. And then for write back, I just need to, I am writing to the register or I'm not. And the data that I'm sending to the register file, is it read from memory or is it from the ALU? And then I already consumed register dest. So the register destination coming out of this pipeline register is just the value of RT or RD, depending on if it was a load word or a R type instruction. So are we all good with this data path? It's very familiar, right? We went over each one of these stages, connected them all for a single cycle implementation. Now we're just adding these registers in between. We all understand that because we have these registers, once we fill up the pipeline, we have one instruction right back, one instruction in memory, one instruction in execute, one instruction in decode, one instruction fetch. What I don't want to see on the exam is my first instruction, it takes 5 cycles. Fetch, decode, execute, memory, perfect. And then after those 5 cycles, I do my next instruction. That's wrong, right? The second instruction starts in the second clock cycle. All right, so this is your question for today. Your code is 798. Do this one on your own. See any new answers coming in? We're close to the threshold, but we're not quite yet. 798. So do talk to the people around you, talk to how you got to your answer, and resubmit if you are convinced to change your answer.
Have these out. There's no second working. It's all right. But usually starts right after the one for each instruction. So which one? This one starts from this one. This one is here. It's like very starting. Some of them don't play this. I remember this one. You still. That's what I got.
Did you change your answer if you were to change? So how do we answer this question?
5 for the first one and then add 1 for all the following ones.
Okay, so you're saying it takes 5 cycles to like fill up a pipeline, right? And then after that 5th cycle, the first instruction is finishing. And then after the 6th, the second one's finishing, 7th, third one's finishing, 8th, the 4th one's finishing, and then 9th, the 5th one is finished. And this is correct. But if I wanted to, if this wasn't very clear to me, right, to do it in this shorter way, then what else can I do?
You can draw it out.
Draw it out. With what?
You can have like a timeline of all the clock cycles
Yeah,
and
I
then
just mean, what was it called?
What?
The diagram.
all the goes in the
The
diagram.
multi-cycle. diagram.
Multi-cycle diagram, right? So it's exactly what you were describing, right? You just, each column is the cycle number, and then each row is my instruction. And I just write out first clock cycle, I just fetch the first instruction. Second clock cycle, my first instruction was in fetch, so now it moves to decode. And then because I'm not fetching anymore, second instruction can be fetched. And then with that visual aid, you can go 1 clock cycle at a time, filling out each column. But this is B. And we'll walk through each one of these snapshots of each column with the single cycle diagram. So this is the single cycle diagram for the first clock cycle, right? I just fetched the first instruction. And all of my other stages are just empty. Second clock cycle. The load word moves into decode. I fetch the subtract. Third cycle, what does the load word do?
Goes to execute.
And what does the sub do?
Goes to the decode.
And then what does fetch do?
Instruction.
What about memory? What about write back?
I've used still.
Nothing, right? So here is the load word in executes, sub in decode, and we're fetching the and instruction. And then next cycle. Someone else? What happens next cycle? What goes into memory? What goes into execute? What goes into decode?
And
What goes into fetch?
more.
Yes. Right? And then next clock cycle, everything moves again, 1 stage at a time. Load word is going to finish, and this is what you were saying, right? After 5 clock cycles, my first one is going to finish. So here's the load word, the sub is right behind it, then the and, the or, and then our final instruction is that we're going to fetch. And now every single clock cycle after this, we're finishing an instruction. Cycle 6, we're going to finish this up. And there's no more instruction to fetch, so fetch is just empty. Okay. Cycle 7, finish the and. Okay. Cycle 8, everything moving forward, finish the or. And then our final clock cycle, we finish the end. So that's how we get 9 clock cycles. So in general, if you have no data dependencies, no control dependencies, your number of cycles for a 5-stage pipeline is 4 cycles to fill, and then plus the instruction count. Because once you're filled, you're going to finish 1 instruction every single clock. Right, so we had 4, because we're a 5-stage pipeline, 4 to fill. And then I have 1, 2, 3, 4, 5 instructions. So that's 9. But we're gonna talk about how this isn't always the case next Monday. And this is the last lecture that you need for homework, as well as this is the last lecture for exam next Wednesday. And on this upcoming Wednesday and Friday, we're going to do review. And also for the exam, the study guide is released. Exam 3 study guide is released. They've all just been there on campus under files. Okay. So after the review on Wednesday and Friday, though, we're going to talk about how this is not always the case, because what if this subtract was reading from register 10? Right? If the subtract is reading from register 10, if I'm in decode for the subtract, what I read from register 10 is the old value of register 10. It's not this, and we don't even have the mean value of register 10. We don't have it until the memory stage. More specifically, until after the memory stage, right? And then what if we have a branch, right? I don't really know what instruction to go next, right? So we're going to start with the data dependencies first, and then we'll talk about control dependencies. And then we'll also talk about how we can speed up our process by not just waiting. So we don't need to wait for the load word to write back its result before we can actually get the data, new data for register 10. We have it here at the beginning of the write back stage. So we'll talk about how we can do that and how we can also do the same thing for, say, an R-type instruction. I have the data for the result right here in the memory stage. So there's no need to wait for me to write it back to the register file. And I'll show you how to exactly do that later on. But for the exam, we're just on the introduction to pipeline. What is the data path? How do instructions and data flow through the data path? And can I calculate things like CPI for a pipeline? Or how do I calculate the CPI? I need to know how many cycles it took, what's my instruction count, right? It goes all the way back to chapter 2, right? So for pipelining, the ISA design is going to affect the complexity of the pipeline implementation, right? So if my ISA says I need to implement floating points multiplication, floating point addition, my pipeline is going to be more complicated. And then what makes it easy? Well, your ISAs can be designed with pipelining in mind, right? So MIPS is a RISC architecture, very simple architecture. And that is because it had pipelining in mind, and with very simple instructions, I get a very simple data path. Very simple data path. It's very easy to split it up. x86 was not designed with pipelining in mind. x86 was designed with multi-cycle. And we didn't cover multi-cycle architectures in this class, but there is a section in chapter 5 on multi-cycle if you're curious about it. And if you also want to come to all files, you can ask me about multi-cycle designs too. But because of that, and how pipelining is going to give better performance, that's another reason that we've also talked about since the beginning of the course, why x86 processors are less energy efficient than RISC architectures like Apple's M1 or M2 chips, right? And they have their upcoming M3 chips, and also our phones use ARM, right? Most phones use ARM. RISC-V is also Qualcomm is making their first chip based on RISC-V right now, releasing it soon. So the other things that make it easy with the MIPS ISA, all instructions are the same one. They all are going through all 5 stages of the pipeline. And we only have a few instruction formats. And then these memory operands only appear in loads and stores. I don't have the availability of, I want to add R1 plus this memory location data. And like we talked about, hazards will prevent next instructions from starting in the next cycle sometimes. And we'll talk about that next Monday. And for next Monday, this is the reading. But like I talked about, it will just have that one lecture of new content just as a buffer before the exam, but all of this content, chapters 6.4 through 6, is for Monday. It's not for your exam.